The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Good evening, everybody. So today we will start with profiling with DL crop, and then we will look into the PyTorch catalyst. So far what we have done, so far we have looked into how to make the entire pipeline for training in deep neural networks. So deep learning algorithms that we have developed so far mostly in the domain of classification, but the same pipeline will be followed for other kind of problems also. So, but in TensorBoard in the last class, whatever we have seen is how we can actually track or how we can see the performance metrics and maybe the graphs for the computational graph for the algorithm and so. But here in DLProp, what we will see is that we will profile the resource usage, the utilization, the recommendation from the profiler. So all these things we will see in DLProp. So this is a new dimension of profiling that we will see today. And data scientists must be aware of such profiling because this will help essentially to improve the training performance in the end. So in today's session, we will see one of such customization which will improve our performance of training module that we will run. Okay, and we will see how much performance gain we are achieving or what are the improvements we are doing. So all these things we will analyze. And also in the next session, we will see the PyTorch catalyst. So this is, as name suggests, it is accelerated framework for PyTorch. This will give you the flexibility to efficiently wrap up everything, whatever you want to do in PyTorch in very simple terms. Okay, so that also we will see. So that way we will get the enhancement of the training modules. So all these things will be very modular, and it will be easy to define the entire pipeline, and also reproducibility will be very, very high. So we will start with DLProp. So let me. So as I was mentioning, that DLProp will help you to visualize, analyze, and recommend. Okay. So what kind of recommendations that we will see, as well as we will see what kind of profile that are coming from, let's say, the CPU usage, the GPU usage. Also inside the GPUs, what are the cores that are being used, how much time they are being used, and how you can improve the performance. Now, in the framework point of view, this DLProp supports also by TensorFlow. You can work with TensorFlow and DLProp. You can work with PyTorch, TRT, also several libraries supported by it because you need to improve some performance and support some backend as well. So DALI, NCCL, so all these libraries are also supported. So today we will see how to use PyTorch modules to be profiled with the DLProp profile. Okay, and so before that we will need to understand a few things. So basically, what is DLProp? It helps us to understand and improve the performance of the DL pipeline, and mostly the training pipeline, because it will be iterated several times, as you have seen. One loop or several loops will be running based on your target run or target achievement. Now, it will also generate reports, visualize the profiles. Now, DLProp CLI, what it uses the Insight System Profiler. So we will enable this profiler to input the profiling data, and it will make the database. Also, it will correlate the CPU usage and the GPU usage, because they both will be working in tandem, and some data it will be shared from or accessed from CPU, and it will be shared to your GPU, and GPU will aggregate or train your model depending on the data which is available. So the correlation between the CPU and GPU will be important, and that will directly get the data from here, as well as it provides to to track your tensor cores usage. So this is very important, because while we are talking about the deep learning modules or deep learning training in particular, so that means tensor cores must be used, right? So because tensor cores are specifically designed for your deep learning computational acceleration, right? So usage of tensor cores, how it is being monitored or how it is being used by your algorithm, that usage detection must be there. So we will see how to track this, as well as so some library that we will be using for enabling tensor core usage. Now, to profile or to see the recommendations, you need to have one recommender system, right? So the expert system provided by DLBlock CLI will provide the recommendations. So if, let's say, your tensor cores are underutilized based on the other cores that are being utilized inside your GPU, so this expert recommender system will tell you that these are not utilized, so you can use these libraries to use to enhance the usage, or maybe let's say you have some data bottleneck or memory bottleneck. So what kind of library you can use to remove that or eradicate the bottleneck? So all these expert suggestions that also will be given by the recommended system, and the viewer will essentially uh, help you to visualize profiles, and also you can log the reports and save them for your later analysis. And also, currently, TensorBoard plugin is also available, so you can use TensorBoard as well to see or visualize the profiles. Okay? So either you use the Aircraft Viewer or you use TensorBoard plugin. Okay? So we will help you to see both, but I mean there will be some instructions to how you can get the profiles in TensorBoard and how you can get the profiles in Viewer. So all these things will. Okay, so as I was mentioning that it supports TensorFlow, TensorRT. So for these two frameworks, you do not need any additional code for modification to be used in DLProf. So it will directly profile the program and it will help you to visualize. For PyTorch, you need to activate this module because this NVTX profiler will be written. So basically, you will enable first, and then you use your training pipeline or your multi-stage pipeline or whatever you want to use for your deep learning training. Now, as I was mentioning in the previous slide, the CLI will process this with DLProf, and Viewer will help you to visualize. So very simple few lines of code you need to add for PyTorch, but that is very minimal, just one. Now, in the previous section, I was mentioning that DLProf, the relationship between DLProf and this automatic precision, mixed precision library is very intact because of the tensor cores. So the profiler actually tracks the usage or utilization of your tensor cores that are available inside your GPU. So that means you want to have some computations to be offloaded into the TensorFlows, and automatic precision library will help you to do that. Okay? So that is why if you are not using automatic mixed precision library, then the tensor cores will be underutilized. So your training layer will have this pipeline. Let's say I have two convolution layers, three convolution layers here, and normalization, pooling, and so on. So all these layers are there from input to output. So this is one forward pass, and this will be iterated several times. Now, what I want to do, I want to convert or scale some of the parameters into some data types that is supported inside the tensor, because all the data types which are, let's say, floating point single precision data type, which are supported in the CUDA cores that are not supported in your tensor cores. Okay? So for the tensor cores, you need to scale your data, which you will use inside your training model to AP16. Okay, so basically makes precision. You will do the computing. Okay, you will use both the data types inside your training to be able to optimize and also get better results in that way, right? So some of the data will be processed in let's say rest of the course, and the scaled data, which is AP16, will be run on the tensor. So that is the purpose of your automatic mixed precision library. Now, automatic mixed precision library has two sources. If you are using NVIDIA, so basically you will be using NVIDIA Apex. And for generalized use of mixed precision library, you can use native PyTorch AMP also. So there are two sources you can use. Either you can use NVIDIA Apex or native PyTorch AMP. Okay, so this is going to be interesting because you'll see that most of the computations which will be run on your tensor cores, to convert them or to scale them, you will need very minimal code as well. Okay, so for use of automatic mixed precision library, it is also very easy. But before going into profiler, you need to know certain things to do and to follow, not to follow, because people often uh, spend some resources, because once you start profiling, many resources will be used. Okay? So what to do? Make sure that your code runs without an issue, because you just check it before running into the real profiler. You just check it whether your training module is working perfectly or not. Just one run will suffice. That without any error, it is done. And also, you need to make a habit of using profiler when you make changes in it, because each change can replicate or can offer you a cascading effect which will enhance the either the performance, or it can degrade the performance. Okay, so several order of magnitude of your performance can increase or decrease. So how your change in the code helps either increasing or decreasing the performance, that you need to check every time. And this is just one rule. If you know that this is going to increase your performance, that is good. But in several cases, you will see when you are working with a big pipeline, you will see maintaining certain aspects of speed up will not be actually happening as prescribed by the library. So they will say that this library will help you to enhance the performance, but in some cases it will not happen because of the way you have defined the pipeline. And so basically you need to check every time whether each change is giving you either your desired performance level. And also you need to get familiarized with some arguments in the DLPROF which will be provided. And of course, the iteration range, delay, duration, etc. also you need to get familiar, because all these aspects. So basically, iteration range, how this will affect your training. How much duration you are actually spending for making certain modules run. So all these things you need to be, at least in some abstract way, you need to. And of course, should not profile for extended period of time, because you should not train the entire thing to get correct profile for your training, because training module is essentially one iterative process, right? And the same thing will be repeated every time. So few iterations, if you check for your training model, that will give you overall idea that how it is going to perform. You do not need to go through the entire training process for all the epochs or for all the iterations. You do not need to do. So few of iterations will help you understand that when it is going to be, uh, it needs some modifications or needs some update. Dual training is repetitive, as I was mentioning, and that is why you need to spend a couple of minutes to profile it, and that will suffice. Also, try to open DLProp database with your TensorBoard or DLProp viewer. Okay? So basically, this the logs will be saved as database, and uh, the recommended systems are TensorBoard and Profiler, so you can use other. Uh, yeah, so it will help to visualize the DLProp event files. So basically, NVIDIA test bench GP plugin you need to use. Okay. So let's go to the demo section now to demonstrate the DLProp, how to do that, and then we will come to our practice. Okay, so let me do full screen. So basically, there are two methods to run DLProp. One is through your notebook and through the terminal. So if you have installed or if you have not installed or if you want to use the DLProp in Jupyter notebook or any other notebook, you can use it. So the method one is essentially the first method, which is used in the notebook. We'll not go into details. You can see the same details in the next videos, next section as well. So in the method two, we'll discuss about how to use in command line. So basically, you need to make sure that you have access in NGC. You need to create one account for that, and you need to have Docker engine installed. And if you do not have, you can check these comments to install it, and then you can install the container toolkit, and you can start using the check the whether necessary drivers are there or not, and then we install the NVIDIA Docker for the so this is the distribution that we want to make available inside my Docker. So basically, you just install it with this command, and then once it is installed, so basically you need to uh, install this package for your use, and then you restart the Docker, and then you start it and just check the version. So this is the complete installation of your Docker, and check the version. And once it is successfully installed, then using this NGC Docker, then we will start using that. So basically, you need to pull the Docker image. Okay, so this is the NGC Docker container for our usage. So once it is pulled, then you can just run this command to launch the NGC container now. And once container is launched, then you can install the necessary package. So what are the necessary packages for here? So basically, you need to install NVIDIA PyIndex, NVIDIA DLProp with PyTorch. You can use also TensorFlow, as I was mentioning. So here we are using with PyTorch. And also you need to install NVIDIA DLPro Viewer, because we are using DLPro Viewer to visualize the profiles. Okay? Now, once you have successfully completed up to this, so basically you have installed all the packages. Now you can use your DLPro in the next command. But before that, you need to have the training.py, because the training module that I want to profile using this DLPro for this targeted workspace. Now, once you have this training.py, so basically let's see what is in the training. So training.py is essentially the entire pipeline for training your deep learning models. Now, some of the packages that you have seen so far, because we have used them. So basically, these imports for your torch vision that you have seen. Few others that we need, some libraries for images and plots. So NumPy, PIL, and Matplotlib. And also you need to import the NVTX. So because this will enable this stack tracer for the profiles that will generate from PyTorch training run. Okay, so this is the only one line you need to add to be enabled, be profiled from this training one. Okay, so now once we have all the necessary packages imported, you just specify the device. These are as usual, nothing new. So all the PyTorch things, train set, data set, valid data set. So here we are doing training and validation. So we are just using the train loader and valid loader with this number of batch size. Now notice that we have not enabled the number of workers. Okay, so we want to see what happens. Okay, now once you have defined the train loader and data loader, you just you can print some images. You can see. Okay, so these are the things that we want to do before going into the training part. So this is the class where we are defining the model. So this is the model definition, and we are transferring the model to the device. We are defining the optimizer, the criterion for the loss, and then this is the training loop that we have defined. Okay? And with torch.autocad.profiler, now we are starting the profiling or emitting the traces from here, because before that we do not need all this. So for this loop only I need to profile, because this is the loop for your training. Now, how many epochs? You just define it. So for, as I was mentioning, you do not need to run the training for all the loops. Just only one single run will suffice, or maybe 2-3 runs. If you want to have some more satisfaction, you can do 2-3 runs of entire loop, and you will get the idea. And this is the validation. Okay. So this is the entire training module which I have written. So now we will go to the code. So basically here, to view the results, you need to run dlprof with this training dot. So this is the command to export the traces into your databases. Then once you run that, you will see that you have, so basically what we have done this, we have so we have mentioned stack function stack equal to true, and it will write all this data into this current directory. And so from the event files, you can see inside the TensorBoard. Okay, and if you have mentioned the targeted files in any elsewhere, you can mention the directory path here. Now, if you are using dlprof, so in our case, we are using dlprof. So the database will be created into the current directory, which is dlprof_dldb. So our deep learning database.sqlite. So this SQLite database has been created, and it is recommended that you open this using dlprofile viewer only. Okay, so because all the necessary encoding and decoding is supported in dlprof viewer. So once you open this, open your profiler into dlprof, then you will see the window. Okay? So basically, you can see that this is loaded from your DL profiler into your local host, and now this is the dashboard for your profile. So you can see GPU utilization and resource usage breakdown, and total kernel time GPUs in milliseconds, and total core kernel efficiency. So how much percentage of core kernel has been used. So now, as I was mentioning that these are the usage and let's take this resource usage breakdown. So 20% resources were being used from elsewhere, and data loader is using 65.81 percentage of resources. CPU is using 13.23, and your GPU is very narrow, so not using tensor cores, because we have not actually used the AMP library for enabling the tensor cores. Okay? So if you go to the recommended system, so expert system, in the bottom you will see expert system, and here are some recommendations you can see now. So the recommendations are 945 operations were eligible to use tensor core, but are none are using FP16 because you have not used AMP library. So the recommendation is try enabling AMP library for more information improvements. And GPU is underutilized, only 5.5% is profile, that is fine. And also, it has recommended that 65.8% of your aggregated run was spent in the data loader, while not simultaneously running the GPU, because it is waiting for the data, because you are not using multiple cores for loading the data, right? So you can either use num cores greater than 0, okay? So these are the recommendations that you are getting, or use NVIDIA DALI, which is the data loader library from NVIDIA itself. So you can use either of them. So we'll see one of them to use. So and also what kind of systems you are using, and what are their versions, and so on and so forth. All the information we get, the guidance here. Since average iteration time is 42 milliseconds, this I mean, you cannot see the graph here, but if you run for more time, like duration in seconds, you can see. So if you run in seconds, you will see what are the use of tensor cores, not using tensor cores, how much memory is being used, data load, IO, CPU. So this is these are the performance summary you will get, and I want to improve the average iteration time in the end, because with some performance tweaking and introducing the MP library, I want to use the tensor cores, and in the end, I want to use, or I want to enhance the average time. So next, we will use the train underscore amp.py. So this training module is using now the AMP library, which is from the Apex. So automatic mix precision, now we are using from Apex, right? NVIDIA Apex. So you can go to this reference. Okay, so the usual Python imports, and then defining the device, defining the data loader, train loader, and everything is same. Only thing is that you need to define this model and optimizer for your from your AMP, because now the model should be compatible to use the scaled data types, okay? And also optimizer, because optimizer is essentially computing the gradients, and then it is being updated with the gradients. So optimizer and model initialization with the AMP, that is important to use AMP library. So we have imported that before, just one more time. So that import was done before. And next we will go to the defining of the criterion, the training loop. Now this is where we are starting the profiler, and then number of epochs we are defining as 1. The same criterion we are keeping to see what kind of improvement we are getting with the profiler. Okay. So x.to device, so data we are transferring to your device, levels we are transferring to your device, the modules, and then we are computing the loss. So basically, while computing the loss, we are now scaling the losses and optimize gradients to your AMP library. So basically, now we are using the mixed precision computer. Now, the mixed precision computing uses, so basically, if you see here, after the scaled loss and optimizer definition, we will just do the backward pass, which will compute the gradients, and then we will update that and initialize them again to 0. So that's the entire pipeline that we have defined now. Okay, so yeah, so this is the entire definition. We just give you one more explanation of this optimization level. Okay? So when we are optimizing, okay, there are several data types that we have mentioned, right? So we mentioned that you can use either AP32, AP16, or mixed of the two. Now, what will be used inside your training? That will be defined by this optimization level inside the initialization. Now, what will be the criterion? I want to have mixed precision computing. So, so there are 4 levels of optimization: O0, O1, O2, O3. Now, O0 is for use. O0 and O3 is without mixed precision. So, O0 is with AP32 and O3 is with AP16, and O1 and O2 is with AP32 and AP16. And based on their usage in training, you will have two models of mixed precision. Okay, so O1 and O2. So which will be better for your training? That you need to actually analyze by maybe 1 or 2 rounds. Okay, so you use one first, then see the profile, and you use O2 and see the profile. Which model of mixed precision computing is helping your case, that you can see from the profile. So that's all about from the profiler, and let's go to the profiles after using the AMP. So after using the AMP, you can see that go to the recommended system. Now it is not saying the previous message, right? So it was showing that tensor cores were not being used. Now tensor cores are being utilized, and it has increased the utilization from 0.5 to 0.6%. So basically, this was just one run, right? Not multiple runs. And data loader has the highest usage. Still, our data loader has highest usage. So still, we have run that without any workers. And that is why you can see here that data loader is using most of the resources, and also tensor cores are being used. So using GPU1, because we are now using tensor cores using the AMP library. So the usage of GPU utilization has been increased, but you can see that average iteration time also have increased, and that is only because your data loader, because of this data loader bottleneck, you are actually increasing the average iteration time, although you are using AMP library. So after introducing the inside your train underscore amp.py. So here now, after introducing the number of workers equal to 4 in the data loader and value loader, we will see that so this was the profiler after that. So now you will see that data loader is now 13% only, where others and CPU usage has increased. Okay, and now if you see the average iteration time, it has been decreased. I mean, almost half. So just introducing one trick, it has increased the performance by 2 times. And you can see that GPU is underutilized, but it has almost doubled the utilization, because now it is getting data simultaneously. So basically 1.2% is the double of 0.6, which was before. But still, we have some bottleneck still because this is a very small network, and so this is how actually you will try to assess, analyze after visualizing. You change your code, use some other libraries, what is recommended by your recommended system, and you increase the usage of your tensor cores that are available inside your GPU. So let's go back to our slide now. So that's all about from DLProp. We will do it today. Okay, so let's now let's start with the catalyst, right? So as I was mentioning that catalyst, as name suggests, catalyst is basically the uh, accelerated PyTorch framework, right? And this was the development was started in 2016, but it has been now it is very mature, and a lot of research and development pipeline using Catalyst. So it is necessary nowadays to understand this framework. So this is a framework for accelerated deep learning and R&D based on PyTorch. And what it helps is that it helps to write your code in very compact way, so that maintaining the huge pipeline of trainings will be seamless, and you can reproduce the trainings, the matrices, the parameters again and again from several runs. So now we will see the training loop. So if you are considering to explore your training module from different aspects, let's say I do not want only epochs to run, right? I want several batches to run, several loaders, maybe from different data sources. I want to load several loaders for each epoch for several stages. I want to have multi-stage pipeline in our training. So now we are getting into some advanced stage, but you understand that the training module is not just only one iteration of epoch. So there can be several loops that can engage the training pipeline for different exploration. So in the end of this exploration, let's say I want to save the best three modules out of that, right? So that is, so all these pipelines management will be abstracted into Catalyst in very simple custom domain. So that is the flexibility of using this Catalyst that we will see. So supported features, as I was mentioning, you have universal train and inference loop. Universal train and inference loop, that is from the perspective of the target. So whether you are doing supervised learning, whether you are doing reinforcement learning, whether you are doing maybe regression, whether you are doing some classification like classic classification, which is also supervised, subset of supervised learning. But whatever you do, it will have one universal structure that you can follow, and also you will have the provisions for callbacks. So once you wrap the entire thing with this universal custom runner, which we will define in the next slide, there will be provisions for callbacks also. So you can also induce some customized things inside the universal training or inference loop. Configuration files for models, and that will help to have wide reproducibility. So if you maintain config file for your hyperparameters, you do not need to change anything inside your training module. You just change the config file for your training, and you just you just have completely another configuration for your training without much of the changes. And best practice for for deep learning is using this kind of optimizers that you are seeing, like Adam W or SWA optimizer. So different choices that if you want to have flexibility in the choices of optimizer, or you want to have flexibility of choices inside the what are the metrics you want to see from the training, all these things you can actually abstract and define with the callbacks. Also, in addition, you will have the support for mixed precision that I was mentioning, that AP16 support, the distributed training support, slum support, and DALI loaders. So DALI loader, that you have seen that NVIDIA DALI loader, it is saying that you use DALI loader, but that support also is available inside this Catalyst framework. Okay? And this is also supported by several backend libraries like AMP, Apex. So these two libraries we talked about just now. And DeepSpeed, FairScale, DeepSpeed from Microsoft, FairScale from Facebook, XLA, so for your Tensor course. So all these hardware backends will be supported from this framework. Okay? So this way it makes Catalyst a wide acceptable framework for accelerating your PyTorch training. Why we are talking about universal training loop? So inference loop essentially uh, uh, will help you to abstract inside your uh, custom runner that I was talking about. Right? Now, runner is an abstraction that takes all the logic. So whether you are how many batches you want to handle, how many data, what kind of model you want to train, even some models if you want to import from the libraries, you can do that seamlessly. And everything, every matrix that are to be monitored, let's say accuracy, loss, precision, recall, F1 score. So any metrics you can think of from a universal training point of view, you can actually have complete abstraction into one wrapper called runner. And of course, there are a lot of more for wrapper, but we will see that eventually. So for PyTorch training, this is simple one batch training for several number of epochs you can see here, and in the end we are printing the training loss. So as I was mentioning, that few statistics you need to print, or maybe you need to give output into your loggers or profilers to be profiled in the end. But to print it every time, whatever you need to track. So if you have, let's say, multi-stage pipeline for a big model, and let's say several other models are also there to be taken into account into several stages, you can see how big this pipeline can be, right? And everything you can just customize into this custom runner, which is either it can be custom runner or superset of supervised runner and other runners also. So you just so this is the universal training wrap up. So basically, you need define the model, which model, criterion, optimizer, what are the train loader, valid loader, or how many number of epochs, what will be the log directory, if you want verbose or not. You just define this, and this will take care of entire uh, loops of or for loop of your trains. So this is just a simplified view of custom runner, but we will come into this in the demo session. Also, in the training stage, you can have logging, model checkpointing, and evaluation methods. Now, if you are a data scientist, for you, not only just model training is necessary. Once you write the model for the training, you need to log your different metrics, and for different metrics, what kind of performance you are getting. As I was showing from the tensor board, right, last time, what batch size or how the hyperparameters help, or combination of hyperparameters. So those were very small number of parameters that we are tracking in the tensor board. Now here you can evaluate without writing any one piece more of code. So all these evaluation metrics that you can think of from any training pipeline point of view, it is already defined. You just need to use that, and you need to use that inside the callback, and also this model checkpointing will help you to evaluate these metrics, because you can have all these metrics stored in several checkpoints and evaluate based on those checkpoints. And also you can select what will be the best model outcome, and those model parameters you want to save it, you just say that inside this framework, and it will do all the things automatically. So let's see one such. So all this runner definition we'll see in this demo session. But as I was mentioning, the provision for callbacks will help you to customize your logic during. So universal training will give you the flexibility to define the universal loops. Now you want more, right? You want to customize your metrics evaluation. You want to log some of the performance metrics based on which you want to evaluate your model in the end. So all this customization you want to do, and that we can do with using this callback. And once again, everything is PyTorch here. So once you are familiarized with the PyTorch syntaxes, usage, and maybe definitions, these are very easy to follow. So the same things will be followed, right? And it provides reusability. It will provide you to define your config file as well. So all these things are there. So we'll just go into the demo session to see what kind of flexibility we are going to get. So this is the tutorial provided by Sergey, who is actually initiator of this project, and now this is global community, completely open source. So you can follow. So all the links will be given to you, and you can follow the tutorial as you are seeing here. Now you have to install Catalyst for ML with all the machine learning components from Catalyst. So it will be downloading all the necessary packages. It will install it, and let's see first classic computer vision classification. Okay. So the same things that we have described so far, like one classification training module. So basically, we are having the same torch and libraries that we have imported so far, and some Catalyst libraries we need. And also Catalyst database has several database support for, let's say, almost all the popular datasets are also available inside this Catalyst database. You can import them. So here we are not using Torch Vision for downloading the data, but you can use Torch Vision. So since Catalyst is being used, you can use Catalyst. So data loader. So basically, with all the transformers we have defined. So basically, once you have you want to define the model and optimizer for your device, just check that whether your runtime is GPU or not. So defining the loaders. So still now we are following the PyTorch. So this is simple PyTorch. Model optimizer, simple PyTorch definition. Then the custom runner definition. So this is the custom runner class, where the handle batch method is the most important batch method, which will define your entire training pattern. Okay. So handle batch has the unpacking of batch, running the model forward pass. So this model is essentially one simple model that we have defined with one layer here, right? Now we have then the train loader loaded, and we are doing the backward pass, then updating the optimizer with the gradients, and then zero grad initialization. So this is the simple training pipeline. Now we want to keep track of loss, accuracy, and so which are defined by this batch metrics update. So here we are seeing that only the metrics that we want to define, okay, and also these metrics will be actually computed and unpacked here, okay. So this batch size for different batch sizes it will run, and in the end we are uh, creating the abstraction. So this is the abstraction creation and hit the run. So this is the runner.train with all these models, optimizer, loader, uh, which will be the log directory for your metrics that you have defined so far. Number of epochs 3, so it will take care of the loop automatically. Verbose true, so we are seeing all these outputs, and valid loader. So you want to validate. So with this valid matrix loss, and we want to minimize the valid matrix. We want to minimize the loss. So this is so true. So you see, the entire pipelines for training and validation is actually defined in this simple training wrapper here with this runner uh, abstraction. Okay. So you can see once we hit run, you are downloading the dataset here for number of epochs. So 3 epochs we have defined. You can see all these metrics that is computed automatically, and it is being logged inside your logs this path. Okay. And based models is being saved here. So based models is 3 out of 3. So basically the third model is the best model, and the accuracy is for your uh, loss is less, and so this is just the 3 epochs that it was shown. So this was a simple pipeline for definition, and more compaction you can do. So if you see this classification, so this is the same pipeline we are doing, but here the same training data, train loader, data loader, and valid loader we have defined. Model, criterion, and optimizer were defined with this parameters, and then we are using the supervised runner as the global or universal training model. Now, inside this training module, we are now defining some callbacks because we want to have the callback for accuracy. Okay, we want to we want to have callback for precision recall F1 score. So all these will be taken care of instantly and without any writing of single piece of code. So all these statistics will be actually stored. So this is the callback support that I was talking about. So instead of only running the module, which is the vanilla module running for this runner, okay, you can add the callbacks as you want to. Okay. So you want to have the confusion matrix callback. So I've added 3 callbacks here. Number of epochs, block directory, and whether this we are doing the validity. Now you can also support different validation metrics also. Okay, so micro averaging, micro averaging, and also the weighted averaging it supports F1 by these metrics. So this matrix is also supported, and you want to do let's say verbose false, and also if you want to do the mixed precision training AP16 equal to true, you can enable it. And since we have enabled it, you can see here that we are actually using Adam optimizer here, but so so once we have actually imported the TL, so everything is imported here. You do not need to import the AMP explicitly, but since everything is imported, so you can use the mixed precision support automatically. Okay, and this will actually transfer the mixed precision support to the native PyTorch support. Okay, so this will not use the Apex NVIDIA Apex library, but it will use the native PyTorch mixed precisions. So one more thing here. So uh, as you are seeing that everything we are logging into this directory here for previous model as well, right? So in the logs directory with custom classification previously, and this is the classification, simple classification with these callbacks. And in the next, we want to do the multi-stage classification. So this is a bit advanced, and this will actually help you to understand the flexibility of using Catalyst in large scale training. Okay. So class customer runner, we are now defining it. So basically, we are defining the engine here. So AMP engine we are using. So again, this is just to use AMP library, and AMP engine will enable the TensorFlow execution. So gate logger will we want to have console, CSV, and TensorBoard available to these directories, and then we want to have multi-stage pipeline for the training. So now we want to have, let's say, two stages of training. Now, two stages means, let's say in first stage we want to do the training and freeze the gradients, and then in the second stage we will use another optimizer and we will tune those parameters and do that. And this is a very like normal way or typical way of training your deep neural networks with at least two stages, okay, to tune for your targeted dataset, because whatever model you are using, that will not be tuned for your a particular dataset, target dataset. So this is a simple demonstration how you can use this multi-stage pipeline or manage multi-stage pipeline inside your Catalyst customer runner, right? And we are saying that each stage will have three blocks, and get the loaders, data loaders, get the model. So get model will define the model, and so basically here the model has two layers, two linear layers, and then in the training freeze stage, we are freezing the gradients where we are not updating the gradients, and here we are using the gradients to tune in the second stage. So basically these are the two stage, and you can see how seamlessly easy to define multi-stage training. Just two lines will help you to enable multi-stage training without. So three epochs we are using. So you can imagine like how this will be once you try to code it from vanilla PyTorch training. Right? Now gate criterion, you just do this. So basically we are defining uh, uh, cross entropy loss and optimizer for freezing stage. We are using Adam optimizer, and for non-freezing state we are using SGD optimizer. So this is also typical practice of using several optimizers into several stages to see what is the performance gain in the end, and or for sure you will get better performance in get scheduler. Now this is to define how these optimizers will get scheduled inside your training pipeline. And now in get callbacks, we are defining all the callbacks for, let's say, criterion, accuracy, optimizer, precision, recall response, score, configuration metrics, checkpoint callbacks. So checkpoint callback will help you to, in the end, uh, minimize the loss and save the best three choices. Let's say I want to save the best four choices, five choices, three choices, or maybe top performant model with this metrics, right? So all this you can do just defining these callbacks. That's it, as simple as that. And handle batch will actually do the training and defining the abstraction and hit the run, and that will do the job. So 1, 2, 3 for the first stage, multi-stage. We will switch to the second stage, training 1, 2, 3 epochs, and you will see the metrics. All the metrics are computed automatically. The accuracy, precision, recall, F1 score. So everything is computed automatically, and they are being logged also depending on the path that we have defined. And the first three best performant model also is saved in this path. Okay? So that's that much of ease you will get using this framework to define the complex pipeline of multi-stage classification or even multi-stage training of your networks, right? Now, to see the logs, again, you can use TensorBoard here to get the profiles. So as you can see here, so for the multi-stage pattern, so basically this is the multi-stage classification that we have done for, okay, right? Yeah. And so you can see after first stage, the accuracy has hopped up, okay? And so this is the typical way of training your um, model. And you can see for all the basically for different parameters, all the parameters have been uh, checkpointed here. You can see accuracy, F1 score, loss, your learning rate, momentum, precision, recall, support. So, and also, yeah. So this is you can just debug it and see what kind of analysis it can do. So this is the catalyst that we are talking. Also, in the slide, if you see, okay, let's go quickly to the demo of. So in this section, we have also given one link for you to refer the catalyst run in. So here we are seeing catalyst run in GPU. You can also refer another link for catalyst run in TPU. Okay, so this is just one or two lines of additional code that you need to do for your TPU, and you can change the runtime for TPU. And in the next week, we will see more of TPU execution. Um, but we will not discuss TPU execution right now, but you can refer to the link for how you can modify your training model for your TPU time. Okay? So to conclude, this catalyst is an accelerated framework for based on PyTorch, and it makes you to write your training loop very easily, and you can do some rapid experimentation, reproducibility, code-based reuse. Also, this is very important because once you have generated the config file, you can just reuse it for different trainings. So as or TA Vidya has written here, I don't know, this is the quote from the initiator, write code with PyTorch, accelerate with Catalyst. Yeah. Thank you with these references, and we will go to the question and answer session. Okay, let me extend the tab here. Okay, I can see all the questions are answered. So now one question is remaining. So is memory pruning advantageous in integrated GPU systems where RAM is being shared between CPU and GPU? Okay. Memory pinning is advantageous in integrated GPU system where your RAM is shared with CPU and GPU. Okay. Memory pinning it may be advantageous, but modern day GPUs use very little of the shared RAM. Okay, so I'm not sure whether how it will help onto training your network inside your GPU. Because once you have uploaded the data uh, uh, inside your block memory of GPU, it will not be shared with your CPU. But yeah, some of the data loaders, if you are using RAM, maybe If you have a very big chunk of data that can be using the shared RAM, but again, this is just the question of experimentation. Okay, so we need to see how the experiments for a particular data set it is helping or not. So uh, I'm not sure whether your memory pinning will help or not. Uh, okay, so yeah, so I think all the rest of the questions are answered. So if you have any more questions, you can post now. We have some time. Okay, so you are asking to share the lecture materials for session 8 and 9, the combined lecture on 18th Feb research session. So I think I request the organizer to take care of uh, this share because I think they have the resources to share. Okay, so I do not see any more questions. So I hope you enjoyed the PyTorch session in these three very compact lectures. So we will see some more of using the next week. I mean, most of the pipelines that you have learned here will be using same pipelines, but also we will be introducing some more advanced deep learning modules apart from classification, maybe just to see how the frameworks are being used in Shell. Okay. So next, I think from Monday we will start TensorFlow. Okay. So with TensorFlow we will see some other pipelines and few advanced usage of TensorFlow for accelerating your deep neural network training. Okay. So thank you for now and see you on Monday.